In this video, we're going to look at how to find the abundances of the different isotopes of an element. Now, we can typically only do this when there are just two naturally occurring isotopes, which is what we have here for boron. Boron has two naturally occurring isotopes, boron 10 and boron 11. If it has more than two, you could still find the missing ones, but they would need to, but not if you couldn't find all of them. If you had three or more unknowns, you couldn't find all of them. They would have to give you some information, some of the abundances. But if there are just two naturally occurring isotopes and we don't know either of their abundances, we can find them, okay? Using our formula for average atomic mass. So we will have two unknowns, but we will be able to create a second equation that relates them. So if you have two unknowns, but you have two equations, you can solve for both of the unknowns using a system of equations. So I'm just going to go ahead and call the abundance of boron 10X and the abundance of boron 11Y. And these are just going to be not their percent abundances, but just their abundances as a decimal. And so if those are their abundances, then according to my equation, the average atomic mass would be equal to the mass of the first isotope, which is 10.013. This is the mass for boron 10. Remember, as I mentioned, the mass number is going to approximately be the atomic mass of that isotope, but maybe not exactly. So it's going to be that times X plus the other one, 11.009 times Y. And then that's going to be equal to the average atomic mass, which in this type of problem, we will have to use the value on the periodic table. So if I look at boron, this periodic table has its average atomic mass at 10.806. So it's fine to use that value in a problem like this. In the problem where it asks you to calculate the average atomic mass, obviously you can't just write the number on the periodic table and be done with it. You can use it as a check, but you have to, go through the calculation with the numbers they give you. But here, that's not what we're solving for, so we really need that number to do this calculation, so we can go ahead and use that number from the periodic table. Now, as I said, we have two unknowns here, X and Y, but because I mentioned that these are the only two isotopes of boron, we know that their abundances will have to add up to 100%. Or if we write that as a decimal, to 1. Okay, so if this is 60%, this has to be 40%. If this is 25%, this has to be 75%. They have to add up to 100% or 1 because they're the only two naturally occurring isotopes of boron. And so then we can write, for example, Y equals 1 minus X. And we can plug that into this equation. So 10.806 equals 10.013x plus 11.009 times 1 minus x. And then we can distribute. Okay, so this is our equation now. I'm going to subtract both sides by 11.009. So on the left side, we're going to get 10.806 minus 11.009. That's going to be negative 0.203. And then on the right side, I'm going to get 10.013x minus 11.009x. That's going to be negative 0.996x. Divide both sides by negative 0.996. And we get that x equals 0.204 to 3 sig figs, which is what we would keep because each of these has 3 sig figs. Remember, the 0 in the front is not significant. So that's x, and then y is 1 minus x, so that y would be 0.796. And then these are decimals, so of course if we wanted to write these as percentages, this would be 20.4%, and this would be 79.6%. So what that means is that 79.6% is Y. Well, what is Y? Well, Y, we established that that was boron 11. So 79.6% of boron have a mass number of 11, and then X was boron 10, so 20.4% have a mass number of 10. Okay, and it kind of makes sense if we look at it because our average atomic mass was 10.806. That number is closer to 11 than it is to 10, or closer to 11.009 than it is to 10.013. So we would expect the boron 11 to make up a greater percentage of all boron atoms than boron 10, since the average is closer to that. And that is consistent with that. So that's the process for finding the abundances of the isotopes of an element when you have just 2 naturally occurring isotopes of that element.